So, so today we're going to be talking about the Lasso. And so I'm not exactly sure why it's called the Lasso, but it's a technique for regression that has some really cool properties. So this will be the last lecture on regression. And this will be kind of a more specialized technique that has cool results. It'll kind of be a culmination of several of the lectures building up to this. And then on Wednesday we'll start talking about noise and outliers, and then we'll have a lecture the following Monday on privacy. So both these lectures will be more kind of fun and more. So kind of more philosophical, not as much kind of here's a technique that takes a whole lecture to describe. So it'll be kind of overviews of large sets of techniques, and hopefully they'll be kind of fun. And then we'll move on to the last section of the class, which will be dealing with graphs and how it's kind of related to understanding, say, the structure of the web and social networks and stuff like that. So there'll be a couple, there'll maybe be one or two technique lectures in that section, but it'll mainly be on understanding the whole structure, the structural idea of graphs and how to think about them, and some of the infrastructure of how to actually process them. So this will be one of the last kind of more advanced, technique lectures in the class. So I hope it's pretty cool. So okay, so just to review, the input to our problem is going to be P, which is going to be, say, this is kind of the notation I've used for most of the class, which is in a D+1 dimensional space. We think of this as a point set. So you can draw in, if you're drawing in, if D is equal to 1, then this is a two-dimensional point set. So if this is D is equal to 1, then D plus 1 is equal to 2. And then the goal is to find some line which kind of fits through this data, and we want to somehow minimize these residuals, which are these vertical distances. So how do we get this out of this data set P? Well, we think of this data set P as being Px is going to be equal to some. Well, it's going to be Px and this row y. So we'll think of all of the first D coordinates are going to be, say, along this axis. This is kind of x, or this is Px, and so this axis is y. We want to minimize the error in this y coordinate here. Okay? And so then we're going to construct this vector x, or this matrix X, which is going to be the all ones matrix, and then Px here. Okay. So this one will kind of serve this special purpose of allowing us to not worry about centering the data. Okay. And then once we have this x and this vector y, the goal is to find set A, which are going to be the coefficients here, which is going to be equal to the A hat R min A. So this is going to be a vector A, which minimizes y minus x A. Okay. So this was the ordinary least squares goal. The lasso is going to be a little bit different. I'll write this up in a second. But just a reminder, we can solve for A as x transpose x inverse times x transpose A. I probably messed up the transposes. Y. Okay, so there's this clean, if you can't see it because of the putting that's in the notes. There's this clean linear algebraic way to just write this, and it automatically gives you the answer which minimizes this. Okay. So this was ordinary least squares. Instead, the lasso is going to instead solve for some a hat, and the goal is to find the vector a, which now minimizes y minus xa. This part is the same, plus this alpha term times the 1 norm of it. Okay, so this is the objective of the lasso. I've added this term here. This is called a regularization term. Okay, and so this regularization term is going to have two really cool effects, and we're going to try and so the point of the lecture today is, one, to demonstrate why it's giving these two really cool effects, and then we'll describe an algorithm of actually how to solve for this. And also at the same point, we'll mention how to choose this value alpha. Okay, so the two effects are that, so remember this is going to be a vector. Maybe I should have written this lowercase a, but so one is A will be sparse. So that means most of the entries are going to be equal to 0. Okay. The second is that it's going to provide a what's called a shrinkage. A shrinkage estimate. This will regress to the mean, and doing this is actually a good thing. Okay, so I need to convince you, and so this is actually good. This is something that we actually want to do. Okay, so we're going to talk about these two properties. So I'll first talk about this shrinkage estimate again. So I mentioned this towards the end of the first lecture on regression, but I'll try and kind of reiterate this because I think the concept can be a little strange if you haven't heard it before, and to spend a little bit more time on it. And then we'll talk about why the sparsity happens. And then when I explain the algorithm of actually how to find this vector, you'll kind of see in action why the sparsity is there. Okay. Just to quickly review, so this is the lasso. There was a very similar thing where we were trying to find a hat, which was r min a of y x a squared plus, where this is the 2 norm, I think should be, okay, so this, maybe this doesn't need to be squared. I think it's not. You can square both of them. I think the math is easier if you square them. It shouldn't make too much of a difference. So this is where this is the 2 norm instead. So the 1 norm, remember what the 1 norm is, right? The 1 norm of A1 is equal to the sum of I equals 1 to D, or D plus 1, of the absolute value of the entry AI. So it's the sum of these absolute values. Okay? Whereas the 2 norm is equal to the sum of I equals 1 to d plus 1 of ai squared, and then all this under square root. Okay? So this one uses the sum of the squares. This is just the sum of the absolute values. Okay? And so this was called ridge regression. And you could solve for it just as easy as the least squares by saying that a hat is equal to x transpose x plus alpha squared x transpose y. So I could this is, okay, so this one was very easy to solve. This one will be trickier to solve because I'm mixing these two norms. This implicitly was a 2 norm, if I don't write the norm. So this one is going to have the same shrinkage property, but not the sparsity property. And we will look at why this shrinkage property is still here, but why the sparsity property is not. All right. Okay. So, all right. So I mentioned a few lectures ago. I guess it was before spring break. So this was a long time ago about regression to the mean. So does anyone remember what that means? Does anyone? So do people not remember what it means to regress to the mean? Okay, and who did not raise their hand? Okay, well that's a pretty good hit rate. So, but who didn't raise their hand even when they did raise their hand? That's a little smaller. Okay, so I think it's worth me trying to explain this again. Okay, so this is kind of actually the whole term regression actually comes from the concept of regress to the mean. I believe I was reading a little history on this. So this idea dates back to I think like the 1880s with Sir Francis Galton. And so I think he was British because he was a Sir. And so what he was studying genetics, and he noticed that. So his initial observation was that he was studying like really people who were really intelligent or really musically talented. So for instance, so people like Bach had children who were also musically talented, but not quite as talented as he was, right? And so there are other instances of these families of these famous mathematicians where like the most senior person was very famous, did a lot of cool stuff, and some of their children did great stuff too, but not quite at the level of the first person in this hierarchy. And so what happened is these really smart people, their children had some of their extraordinary talent, but not all of it. Okay, but this was kind of hard to measure and quantify. So he was trying to look at more quantifiable things, and he was looking at height of people. Okay, so he took, if you looked at, you have two people, and so you have a father and you have a mother, and so both, they come from populations with, say, an average height. And so say the father was +2 inches. So he was +2, so it was above the average height of the population. And the mother was also +2 inches. Okay? So then, the thought is, what is the expected height of the child? So relative to the population. So there's lots of factors. if you look in certain parts of the world, some people tend to be taller than others. But if you normalize by the population, they should have some, basic genetic makeup. They come from a population and there's some variation there. Both the father and the mother were above average. So what do you think if they have a son, you think it'd be maybe roughly the father's height, maybe plus 2 inches. Well, so there's a mean height. So say the average height was, this is probably not true, but say for average men it was 6 feet. And so for the average father and mother, it's like male and female. Okay, so the father and the mother, and so maybe the average females was 5 feet, and so if they have a son, you might expect that the son would also be 6 feet and 2 inches, where this was the average. So it turned out that the average son would be something like the mean of the distribution plus the average of these two additions, so plus 2 inches. So say the average of these two times about 2/3. Okay, so they kind of were closer to the mean than both the mother and the father in expectation. And this was kind of surprising. You might think if they were both plus 2 inches, you would expect the child would also be 2 inches, above the mean. And so this was kind of, slightly confusing. So Sir Francis Galton, who studied this, did never come up with the right biological explanation. He thought you got some genes directly from your ancestors or something like that. It turns out there are lots of factors which kind of cancel out or kind of recessive. I guess they do kind of come from your ancestors, but those kind of, in order to be 2 inches above the average, you need to have a lot of these kind of random events happen. And when you mix together random events from the mother and father, some of them cancel out. Okay, and so there's this thing where the son is more likely to be closer to the mean than both of the parents if they are kind of these exceptional people, these kind of people who are higher above the mean. You'd expect their children to be closer to them. So this was one of the first concrete examples of this. So let's try and go through another example. Okay, who knows? So who knows the rules of baseball? Okay, who doesn't know baseball? Now, do you know cricket? No baseball, no cricket. Okay, so say it's like soccer. Okay, so people are scoring goals, and so the season is split into 2 halves, or someone someone has a batting average in baseball, or they have a rate of runs in cricket. Is that what you call it when you go back and forth? Runs?
You can call batting average.
Oh, okay, the batting average. Okay, good. So there's a batting average, and you look at the whole league, and so you take the league and you look after the first half of the season. So the first half and then the second half. Okay? And so the first half of the season, you look at the leader in the batting average. Okay? So the person who has the highest average that part of the season. Okay? So in baseball, you would say maybe someone was batting on 350 at the first half of the season. This would be a very good batting average. But say over their career, they had batted 325 on average. Right? So that means 35% of the bats that they didn't walk, they got a hit. So what would you expect their batting average to be in the second half of the season? So people think it's, so that you might think it'd be the same, but it's almost always is the case that it's a little worse. That's right. So it's somehow back down towards the mean. So what probably happened is this person got, you know, in most kind of phenomena, there's some element of skill and there's some element of luck. And if you are the very top, you probably have skill, but you also have luck that part of the season. And this luck is kind of some random occurrences. And so in the second half, the luck is random, so you should not expect to get the same luck that you got in the first half. You should expect to get an average amount of luck. And so because this person was the leader, they probably had some luck. And so they're probably going to do a little bit worse because they probably have less luck in the second half of the season. So if you look at some of the more kind of the better statistical ways of modeling sports nowadays, they build in some luck factor. How much luck has this person supposedly experienced so far this season? And then they try and factor that out in future future predictions, because you can't count on this luck. So it's not to say you'll have bad luck, but it's to say that you can't expect to have the same luck that you had before. Okay, so again, this was really high, they're regressing towards the mean. The same thing may happen if someone was the lowest batting average. They probably were unlucky, so in the second half they probably have a higher batting average. Okay, so another example is if you're taking tests. So let's say I gave you all I gave all of you a quiz right now, and it was a really hard true-false test, and and I gave it to you, and there are 10 questions, and no one knew any of the answers. So hopefully, it's not the case. Hopefully you're able to know some of them, but you had to guess on all of them. Okay, so I took the class, and I said, let's look at the top 10% of the class. And these people scored on average 75 or 80% on the quiz. But this was blind luck. They probably should have guessed 50% on average. Now I give you another quiz, equally hard. Again, you have to guess. This top 10% should not be able to do, you know, we should not expect that same 10% to still get 80% on the test. They're probably on average going to get 50%. They're going to probably regress towards the mean. They got lucky in the first half, and the second half you should not expect the same luck.
It seems like it contradicts the gambler's fallacy, where if you see 20 heads in a row, then you're going to bet a lot of money if the next one's going to be tails, because it's going to even out eventually. It's just not a big enough set in that case.
So that's, you probably shouldn't do that. So you probably shouldn't bet money that it will be tails, because the past, assuming that all the events are independent, the past should actually have no consequence. You're still equally likely to get heads and tails after you had 20 heads in a row.
But doesn't this say that eventually it should even out?
Well, this is saying that what's happened is some component is skill, some component is luck. And if we take the extreme people, they probably have luck. So another example is a test where, say there are 10 questions, and half of them are really easy, and everyone knows the answer. I say, the answer to question 1 is true or false. Actually, both true and false are correct for that. So anyway, say half of them are easy, half of them are really difficult, and you need luck to get them right. So the average score will be 75%, because everyone will get 50% right. That's skill, and then everyone will guess on the other. So some people will get 90 or 100%. 25% of that was luck, 50% of that was skill. If you gave them another test, you'd again expect them to get 75%, independent of what they got in the first part. So even though I'm taking the extreme people here, these I expect, actually, if I tested them again, to have a smaller net. Okay, so what does this have to do with regression? Okay, so I tried to draw this before, so let's say I have some data where it looks kind of like this, but I have some outlier point down here. Okay, so if I do so probably my fit should probably go through here, and I should kind of ignore this outlier point. But if I do ordinary least squares, I'm probably going to get a line that's going to go like this. So this will be the least squares solution. It's going to be pulled down closer to this onto this outlier. So, so I'm going to have this error here. So what this model is saying, that for this x value right here, I'm predicting the y value is on this line, okay, based on this data point. But this data point was one of these extreme cases. If I were to test at this y value again, I would expect to be back to where the mean of my data set is. There's some skill. The slope of the line is positive. That means the larger the x, the more skill I'm predicting. But part of this is luck. Or part of this is random noise. And so I expect this random noise probably won't occur so low again. It'll probably be distributed like the rest of the data. And so I'm going to guess that this random noise was small, so I'm going to, actually I drew this picture in a way that doesn't illustrate this well. Okay, I'm going to try and draw this picture over again. Then I mentioned there's this weird thing where all the examples look like this, because I needed to fit this on the board. But okay, so I have to draw this over again. Okay, so my data is going to be smaller. It's going to look like this. Smaller here, okay? And so the best fit line should be through here, but maybe I have an example, and the noise is going to be such that it affects this line. So it needs to be pretty far away from the rest of this data. So it's either going to be really high up on the chalkboard, or it's going to be really low down here. Or maybe it's on this side it's really high or really low. One example would be up here. So let's assume it's actually really far up here. Okay, if it's really far up here, so let me draw this as a green point. Then what's going to happen is my slope's going to be like this. If on the other hand, it's really low down here, then the slope may actually be kind of like this. I may actually make the slope so it's negative, it's that far down. Okay, so if it's a really far outlier that's actually affecting this curve, then it's going to be pulling it really far away. Okay? And so in both cases, if it's really changing the slope, then my guess should be the true slope should be back towards this middle here, back towards a smaller slope. So I want a slope that's closer to 0. So I want a smaller slope. Okay, so what this is doing, this minimization, it's saying I want to minimize this plus this extra term. And these coefficients are determining the slope. The larger these are, the larger the slope of the curve. Meaning the more I change the x-coordinates, the more affected the y-coordinates are. Now, as kind of a baseline solution, I'd just say there should not be any effect between x and y coordinates. I haven't demonstrated this. So my baseline is that there's no correlation. And that would be zeros for all these coordinates. So that would make a line perfectly flat, and this is kind of going to be the mean, a line that's perfectly flat, that there's no correlation. And so regressing towards the mean is pulling these slopes back towards this one in the middle. So if your slope really was really high, then your data would be kind of like this. But you're trying to predict this. Remember, we're trying to predict the y-coordinate here. We don't care about the x-coordinates. If you're doing PCA, you're doing something like that. But we care only measuring this y-coordinate. And so then a line that looks like this is going to be really unstable. Because this point, its predicted value may end up being all the way up here where these actually meet. It may not meet until way up there. So this is a really noisy situation. So you want it to be flatter, you trust it a bit more.
Is A the slope?
So A is the slope of every coefficient here. So this is describing for every column of x, you're kind of scaling that column. And then you're adding together these scaled columns. And the coordinates of A are telling you how much to scale each of the columns of x. Okay. So so hopefully you kind of believe that you should want if you don't know anything about the data, you should want a smaller slope. If you think there's noise in the data and you're going to err in some direction, you want to err in terms of having a smaller slope rather than a larger slope. If you don't know anything about the noise. If you have a data point here that's pulling the data slightly down, well, you don't know if this is the noise or some of the noise is up there. There's no way of really knowing that ahead of time. You just know that there's some noise in the data, and in that case, you should bias the slope to being a little bit smaller. Okay, so I haven't told you how much to bias it, or even how to find the solution. But we'll see how to do that partially in this lecture, and we may continue it in a little bit into the noise section of next lecture. Okay, but we want to do this shrinkage. This is kind of a powerful way to get rid of noise, and this will make this more robust to noise, and we'll mention this, describe this a little bit more on the lecture on Wednesday. Okay, so the second aspect of this is that this, the solution will be sparse. Most of the coordinates of A are going to be 0. Okay, so I'm going to try and draw a picture which will hopefully explain this. Okay, so I first need this, an equivalence between this formulation. So there, for all alpha, there exists a beta such that A hat is equal to the R min of A of less than A. Okay, so I first need to convince you that this is true. And I mentioned this before, but let me try and convince you again. So this is saying that this, so for every value alpha I used in this expression before, there's a value beta such that I want to find the minimum least squares solution such that the norm of A, the one norm of A, is less than beta. It's less than some constant. Okay, so why can I see that this is true? Well, if I can say, well, let's actually solve this for my chosen value A. And then given that solution A hat, I will just set beta equals to A hat 1. So it should be less than equal. Right? So if I solve this expression over there for alpha, then I just set beta equal to this, right? And then it must be true. Right? So now if I make alpha larger, so that will force this norm to be smaller. So if alpha is larger, then beta will need to be smaller. So there's a correlation. As alpha gets bigger, beta gets smaller. There's a one-to-one correlation. Okay, so now this, for the ridge regression, this I know how to solve. This I don't know how to solve, but this form with the beta, I do know how to solve. And I'll show you how to do that. And this will also explain why we're going to get a sparse solution here. Okay, so try and draw this picture here. So we're going to write A here. So A will be so this is going to be A with the solution of A with least squares. Okay, so our data may actually live. Okay, and so okay, and so this point is going to be the origin. So this is going to be the solution of all zeros. So this is going to be the space of all solutions. So of all possible. Okay, and in this case, it's only going to be 2 dimensions because that's what I can draw, but we'll think about how to imagine this in higher dimensions. Okay, and so now I'm going to use this beta restriction to put a bound on the size that this norm can be. Okay, so if I'm using the 2 norm, I'm going to get this circle here. So this is the 2 norm here is equal to beta. And if I use the 1 norm, so this is A1 is equal to beta. And everything inside that is less than beta, so the viable solutions for the 2